I'm going to talk about Monte Carlo method and temporal difference. This will be the main subject of class today. Once again, I would like to start from the basic architecture of transformer model. We have agent and we have environment. Environment is represented by state. If we have an agent, we make an action A and we look at the reward. If your problem is very small problem, we can use the tabular method. However, if your problem is very big, like a Go game or foundational model, we have to use the deep neural network. So the purpose of our reinforcement learning is actually to train deep neural network. In order to do that, later next week, I'm going to show you what will be the loss function and how we will apply the backpropagation. That is the main subject of the class next week. Especially in these days, for this agent, we are using transformer network. This transformer network will make sequential decisions. By having iterations, we're gonna have optimal decision. Once this agent is well trained, this agent will make a best decision instead of human being. There are many different types of environment. One of them is game, or the other one is foundation model. By applying this reinforcement learning method, we can win game because we know what is the best decision, or sometimes we can make foundational model more robust, ethical, and economical. The beauty of this reinforcement learning is it can always find the optimal solution for human being. The disadvantage of this reinforcement learning is there are a lot of iterations. That means it is very heavily computing intensive. And also, sometimes we have to calculate reward. That takes a lot of simulation time. Because of that, it is very computing intensive. In addition to that, when we are making the action in the foundational model, in order to obtain the reward, this foundation model itself has huge amount of iteration inside because we have to apply the backpropagation or inferences. And in the case of transformer model, we have to do the self-attention and cross-attention, and there are huge amount of computations are involved. And also the number of tokens are now in these days 1,000, 2,000, but sooner or later it is going to be a millions of number of tokens. So it is very computing intensive. That's disadvantages. As I mentioned before, sometimes we have small size problem, and then we can apply the tabular method. If the problem is large size problem, we have to apply the deep neural network. Another observation point to look at the reinforcement learning is that sometimes we know the model. We know what is the probability of action. At each state, sometimes we know what is the probability of action. But sometimes we don't know. We do not know about probability action. In most problems associated with foundational model or engineering problem, we don't know what is the actual probability. In those cases, we have to apply the Monte Carlo method or temporal difference method. So major focus of reinforcement learning in this semester is to apply the transformer model network as an agent for the case of model-free case. That means we have to be able to combine deep neural network with the Monte Carlo method or temporal difference method. A few years ago, AlphaGo was introduced. They played the Go game with human being. They were using, at the time, CNN type of agent network with the Monte Carlo method. Because when humans are playing the Go game, we don't know what next position the Isidore will put his white stone. Huge number of uncertainties. Then we have to apply the Monte Carlo method. That is the main subject of class today. When we are applying, this reinforcement learning, we have to know certain definitions. First one is value function. Value function is summation of future reward. Value function is not looking at what we have right now. It is looking at what we're gonna have at the next state, after that, a step after that, until the end of the episode or experiment. If this episode is infinite, we have to apply the Monte Carlo method. There are certain terminations, like Go game, we have to apply the temporal difference method. Here we have pi means the policy, and policy means the probability distribution of state transition. Sometimes it is known, sometimes it is not known. Anyway, this expected E means expected value when we are following this policy pi. Here, the summation of total future return is called as, reward is called as return. The purpose of this reinforcement learning is to maximize the return. Return means the future reward, summation of future reward. But the interesting thing is that future reward that is called return is the reward at the next step and the value function of next step, because this is the sequential addition. So this is being called as Bellman equation. So when we are applying this Monte Carlo method or temporal method and to derive the backpropagation equation, this Bellman equation is most fundamental equation to be used. Why Bellman equation we have? Because it is a sequential addition. So the meaning is that our value function is expected value return at the next step, and if we know value function of next step, we can obtain the current value function. So I know value function. If I know my future, I go just one step and look at the future. Oh, that's bright. And then I can see all the futures. That is the basic concept of this Bellman equation. Another Bellman equation is action value function. This is called as action value function. This is called as value function. Another Bellman equation is that extension of this value function at a state st, if we make an action, what is the expected future reward? This action value function is the subset of value function for each different action. If I make a movement in the east side, I can see what is the future. If I move to west, I can see the future. If I see the north, I can see the future. Each action will give different value. That is the action value function. But summation of east, south, west, north, I see what is my future. That is the value function. In the previous class, we applied the tabular method for the case of model-based case. We start from here, we end here. And north, south, east, west has the same probability distribution. In the previous class, we solved a problem in each case we know action probability. Means east, north, south, west has the same probability. That is the model-based case, and small size problem, we're gonna use the tabular method. And what we found is that after applying this Bellman equation, that means if we know what is the next value function and adjacent and multiply by 25%, we can update value function until it saturates. And we found that it is like initially all this value was 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Initially, all the value function was set to 0, and then one by one, we apply this Bellman equation because at each state they have east, north, south, west. They can calculate future reward. Then they update. But this number endpoint is always keep 0. Because of that, after 100 times of iteration to apply this Bellman equation, finally we got certain numbers. Minus 30 means if our decision action is random, east, north, south, west is equal to same number, the number of steps from this point to end is minus 30. So this is the way we can apply the Bellman equation to obtain the value function. Then what we are going to do is we can make a new policy. We make a new policy which make a direction from to the nearest smallest number, like that. So updated policy will be like this shape. So our initial policy was just random policy. Initial policy was random policy. When we start from this point to that point, what it would be optimal path? That was the question, and that was the goal of our reinforcement learning. Initially, we choose policy of random direction, random action. And we just keep calculating the value function by doing iteration. Eventually, we're gonna have value function table. From value function table, we can update the policy. That is the optimal policy. Here, we choose an action direction from current position to nearest best position. We choose action north, south, east, west equally. But eventually what I found is that north is the best direction. Because in the north direction, our total return reward summation is maximum. That is new policy. And now we got new policy and we can get new value function table. we first initialize this table with 0, and we start with the random decision policy. And we calculate value function based on this action, this policy, random policy. And from this updated value function, we update new action table. Then we calculate new value function from the update policy. By having that, what we can see is that by following this optimal policy, number of steps from this point to the end is just 6 steps. Because we just follow this process. Go, 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 go. 1, 2, 3, 4, 5, 6. Compared to 47.4 steps. This is the way the reinforcement learning is to find the optimal solution. In a case of model-based case and small size. Because this is a small size problem, we are using the tabular method. And because we know the probability actions looking at these arrows, we know this is model-based case. But actually next week, we're gonna try to unknown model-free with a large problem using the transformer or CNN type of network. But basic concepts are here. So initially, we calculate value function. From the value function, we update policy. And with updated policy, we calculate value function. And using the updated policy, we can value function table, we can update policy. And eventually, we're gonna go to optimal policy and optimal value function. If you read a book, 500-page books of reinforcement learning, this is the sequential of chapters. Once again, I would like to summarize for this case. I haven't started Monte Carlo method or temporal difference method, not yet. Now this is the model-based case. That means we know probability distribution looking at each arrows. Second, this is the 4x4 matrix problem. The number of unknowns are just 16. Very small size problem, then we can use this whiteboard or blackboard. In those cases, by alternating calculation of value network and policy, we are sure will be reached to an optimal point. That is the goal of this reinforcement learning with a huge number of iterations. And the reason, the background, to be able to calculate this value function table is because we are able to use the Bellman equation. Just looking at adjacent cells, a value function, we can update easily. And that is why, because our definition of value function is expected summation of future rewards. So because of that, even though we move one step and looking at the value function, we can, by exploring different actions and doing all the summations, we are able to get total value function. Because chain rule is hidden in this definition. If the value function definition has different forms, probably we cannot use the Bellman equation, and probably we may not be able to use this kind of method. Thank you for your kind attention. Now, let's move on to unknown problem. Model-free case. Model-free case means we don't know the probability of action. In this point, our probability of action to the east is 100%. Here, 50%, 50%. Here is the 50%, 50%. But in this policies, all the east, west, south, north is 25%. This is the model-based case. But unfortunately, what I'm saying is that in most human engineering problem, there are so many states and unknown parameters. We don't know what's going on inside, especially in the fundamental model. There are billions, hundred or thousand billions of parameters are there. And even though we are applying the noising and denoising process in the diffusion model, and we are imposing Gaussian distribution, and also we are imposing entropy, that works well. But many cases, we don't know why. So it is a kind of unknown model that is model-free case. Then we have to apply the Monte Carlo method and the temporal difference method. And I'm going to spend some time today to talk about that. First, I'd like to talk about Monte Carlo method. Still, I'm going to apply it for the small size problem using the tabular method. Next Monday, I'm going to use the deep neural network. But to build up the basic concepts of Monte Carlo method, I'm going to start with this tabular method. It has as state S0, S1, S2, S3, S4, S5, S6, S7, S8, S9, S10, S11, S12, S13, S14, and N. We start from here. Once again, we don't know what is the probability of action. We randomly choose action. We can choose action by random method, random. At S0, we can move to S1 or S4. Probably we just choose randomly. Sometimes we are using previous experiences. Or at this moment, we are not going to go through that. Random, or we may have some references. But that is the key concept of reinforcement learning. But at this moment, we are not going to go through that. This is the offline method. And sometimes we can have online method. When I make a decision, sometimes I feel good, I go to east. I feel bad, I go west. It's a kind of random. But sometimes I talk to my friend or my wife or my former advisor, should I go to east or should I go to west? Sometimes we can learn from somebody else. Even though there is not known probabilities, but we can talk to somebody else. That is the way of offline method. Sometimes I feel good, go to East. Even though I don't know exactly probability, but I make my own decision, that is online method. Sometimes I go to other references, that is go to offline method. Imitation learning is a way of offline method. I'm going to go more details about in this unknown probability distributions, we have to make a decision for Monte Carlo method, and I'm going to talk about that next week. But anyway, I go through let's assume I randomly choose south and east. At state S0, I choose goes to south. S4, I choose goes to east. East, south, south, east. 1, 2, 3, 4, 5, 6. After 6th step, I reach to the end. There might be hundreds of different paths if I choose randomly. Then I record it to as like that. Because I took this experience, I record it to this pair. Monte Carlo method is a kind of taking some experiment. I don't know what is the best answer. Just try it and record its scores. We just try only one experience, and each step we have different numbers. From S14 we move to one step. From this point we have two steps. Because of that we put the value -3, -4, -5, -6. So this model-free case of a Monte Carlo method, we don't know what is the best and what is the probability. We just try. We go through that, and we decode that experiment into this form. After each episode generation, number is updated by adding new number, and value function is updated by averaging average number. So basic concept of Monte Carlo method is we take many different paths and many different experiments. Let's assume that you did 1,000 times of experiment, and total is becoming 1,000. In each cases you add value, and finally you make average. So here we have two concepts. One is experiment. Second is average. Surprisingly, after you do all this experiment, you're gonna reach to the optimal value. Once you reach to an optimal value, you can decide optimal policy. Now, I have to make decision east, west, south, and north, and I don't know where to go. This is model-free case, but I don't know what is the future. The only way is we go up to the end, up to the death of our life. At this moment, I have to choose what I'm gonna do next year. You may choose different company or different schools, or every day you make a decision. But sometimes you don't know what is the best. Even we don't know definition of best. Is that good for my happiness? Is good for my wealth? Or is good for my father and mother? What is really the best for me? That is the starting point. That is the definition of reward. And then we don't know which direction is best. The concept of Monte Carlo method, you go through all the process and come back and you try another paths. You try another sequence of decisions. You try it again, and you make an average. Then expected reward into north direction, south direction, east, west will be obtained. Based on that, you can make a decision. So huge number of iterations will be needed. In the cases of model-based case, because we know the probability distributions and we can choose actions when we are calculating the action value function, we follow the probability distributions. But here, even we don't know what is the probability distribution of action. So we have to make many different episode generation. We have to many experiment. So it's very computer intensive search method. And AlphaGo game, they used this Monte Carlo method. Between the time Isidore is making the decision, AlphaGo itself has thousands of computers. They are doing all this Monte Carlo simulation. What if the probability of winning, I make this decision, and they go up to the end of the Go game. Thousands of GPU are doing that. So behind the AlphaGo, thousands of computers are doing the Monte Carlo simulation. And Isidore is doing himself. That's why AlphaGo has superior than the human being. But it also, again, is very computing intensive approach. So when I make an experiment, so one condition of this Monte Carlo method is that it has to have an end. So it is terminating episode. But sometimes some problem we may not know whether it is end or not. So the only case where we can apply this Monte Carlo method is because it will be surely ended up to certain steps. And when we, at each experiment, we have to make certain actions to build up these experiences. Those actions could be decided by his own decision, or sometimes I'm looking at other tables. For example, I have a friend who did all this experiment last year, 1 year older than mine. I look at his table and I choose his action and I make this episode. That is offline method. But if I follow exactly same policy as my friend, my life will be the same. So sometimes I have to have certain deviation. Sometimes I have to make some different decision compared to him. That kind of 1% or 0.001%, you have to have certain variations. And that is called exploration. 100% we are following my former advisor, that is exploitation. So probably when you are making a reinforcement learning programming, probably they may ask you what is this deviation epsilon at that kind of. How much you're gonna, totally you can choose your own, but you may have certain offline references. Now, let's go to temporal difference method. Temporal difference method is useful for unterminating episode. We don't know if it will be terminated or not terminated. And in order to apply the Monte Carlo method, you have to go through all up to the end. But temporal difference method is, if you are here, you just make a 1 step or 2 step. Rather than going up to the end of our decision, you can go to 1, 2, 3 step. Come back. 1, 2, 3. More careful experiment. And then in the previous case, I had 1, 2, 3, 4, 5, 6. Sometimes if you choose different policies, sometimes you may go through again and finally come back. So it takes huge amount of computation. So temporal difference method is little bit careful algorithm. You just move 1, 2, 3 step and then making average. 1, 2, 3 step and making average. So a little bit careful and time efficient method, especially whether it will be terminating episode or unterminating episode, we don't know. Then we're applying the temporal difference method. So next week, I'm going to go to very large problem. Then we have to use the deep neural network to represent agent. So this purpose of this reinforcement learning is training this agent. Then we have to define loss function. Loss function will be this value function. So without to apply the gradient descent of value function, we have to be able to calculate the value function. One way is Monte Carlo method, the other one is temporal difference method. And I'm going to go through that in the next class. Thank you for your attention.